It's a great honor to be elected as a fellow. And here I have taken this opportunity to briefly introduce myself, my background, and also to see what I can contribute to the academy. And I'm originally from China. I got my bachelor degree in hydronic engineering. I went to the United States, got my master degree in civil engineering, and then PhD in structural engineering. I have also have got two minors. One is seismology, another one is mathematics. So I worked in China, in United States, in Singapore, and migrated to Australia in 2002. As an academic, has always been an academic, do both teaching and research. I also provide quite a lot of professional services. And also been serving in editorial board of many international national journals. Currently, I'm serving actually more than 10. My research, basically, I'm interested in structure protection against nature and man-made dynamic nodes, and also structure health monitoring for better engineering asset management to prevent catastrophic failures of structures. So focus areas in basically three areas: blast impact engineering, and earthquake engineering, and structure condition monitoring. I use this to explain. Say, assume we have a flying disc in air. No matter how hard you push it, you only move it. You can never break it. But if you shoot it by bullet, you break it straight away. And that is the same structure. The structure response basically depends on how fast your loading is applied. So my my research covers the entire spectrum. If it's a static, basically it's covered by the displacement is Hooke's law. If it's very, very fast, it's covered by the wave propagation is Newton's second law. So it's if in general it's in between. You see, if we have in the I put there one is typical Oklahoma building collapse by the blast loading. It's stand straight, the building, and if it's a typical earthquake collapse, the building actually shift around. It's a displacement government. So I cover entire this spectrum, different loading rate from a static to very, very fast blast. My work start from modeling the dynamic material properties. They are very, very different. Depends on the loading rate. Materials change, its property change from static. And then those are some examples we tested recently. And also modeling the shock wave propagation in interaction with the environment to modeling the blast loading, ship impact or vehicle impact to model what is impact loads, and do the probabilistic seismic assessment to predict what is seismic ground motion. And current work include the predicting the ground motion at the subsea level, not on the ground onshore. It's a offshore ground motion. And so with the proper loading, then we can do both the experimental and also numerical predictions, developing numerical model to predict structural response, and also do the structural strengthening. This is an example of use FRP strengthening of concrete or steel structure, and do the life cycle performance prediction, considering the structure deterioration due to fatigue, due to corrosion, what is the current status and what is the current performance and load carrying capacities. And also do the vibration control, that is how we can control the vibrations, and do the structure health monitoring. And current project we work on using big data, use the deep learning, and also try to develop more sensitive damage index, quantify the structure condition, and do the both vibration-based and wave propagation-based structure health monitoring, and also developing some sensors for better measurement of structure performance. As for working with the academy, I look at the academy's identified national technological challenge. I think I'm interested. I could contribute in Challenge 6, infrastructure to meet Australia's future economic and social needs. And mankind started to build structures thousands of years ago. Some of them still stand, like a pyramid, Great Wall. But we always ambitious to build structures longer, taller, aesthetically more appealing, and also build structures in a harsher environment. But on the other hand, we have many new materials come in, and like nano, graphene, polymer, these materials, and also have many new structural forms, metaform, aesthetic structures, lattice, smart, composite. How we can make use these new structure forms, make use new new materials to build infrastructure. That is my research interest, and also I think we can work on that to build safer, resilient, and more sustainable civil structures. That is the area I'm interested to contribute. Another area, I've been an academic doing teaching for many years. I've been always thinking like our current undergraduate students, because of the internet now, internet development, our students are a lot more knowledgeable compared to when I was a student, because they can get information easily, a lot of the information quickly from internet. But looking at the knowledge, what they get is quite fragmented, non-systematic, and quite often lack of in-depth. So that affect their ability to, not necessarily to say to do research, and also lacks the ability to learn by themselves in the future. So I've been thinking what we can do is try to develop some new curriculums and or teaching methodologies, how we can prepare our engineering graduate students, because engineering students, because they're going to have 40 years or so professional life, how we can prepare them to face the challenge in the 40 years time. So that is the area I'm interested. I hope I can contribute. Thank you.